Is there a new Google Classroom for this semester?
Sorry, could you say that one more time?
Is there a new Google Classroom for this semester?
Not yet. There will be, and I'll send out that information soon.
I have another question.
Yeah.
Where were we supposed to turn in the participation thing? 'Cause I didn't see it.
So my hope was that we would, like, for in the classroom, we just hand it in right at the moment. But for online, you can just email it to me. That could be snap a picture and email it, or share a Google document. Either way is fine. And that's still open. So if you didn't get that in yesterday, go ahead and send that in, and you can get credit for it. So good to see you all. Kind of a rough day outside. Ever tell you, like, my second year here, I was trying to walk back from the dining hall to class, like over one of those, on a day like today, on the snowy hill, and I just completely slipped and like slid like halfway down the hill, and like all my clothes were ruined, and it's like, man, I haven't slipped again yet, but makes me more careful. So last time was sort of a review from last semester because we talked about factoring, but we also snuck in some new factoring problems that we hadn't talked about yet. And that was on purpose, just to kind of confront something new, because that's kind of fun. I mean, I wouldn't want to be graded on confronting something I'd never seen before, but I also think it's fun to just like try new things and see what we can do. But for today, let's do a little bit of, I don't know what you want to call it, like guided meditation, guided mathematics. I'm going to do some stuff on the board, and I hope that you'll do it on paper with me. Also going to try to make sure that I can fix this sound, because the wrong mic was on yesterday, and when I went back and looked at the video, I was sad that I wasn't giving my online students as good of an experience. So let's do a mic check. So can you hear me like normal right now, if you're online?
Yeah.
Okay, good. Here's what I want to do. So go ahead and take out your paper. Write down a X and Y coordinate axis for me. We're going to use these mainly for sketching. Like if you wanted something to be really perfect, you could use graph paper, but I think it's a good idea to get into the habit of just being able to quickly sketch something, even if it's not exactly perfect. I'm going to write down two equations. Here they are. X plus y equals 2, and 2x plus 7y equals 9. This is a system of equations from the book, but we're going to do some different things with it. And so the first thing that I want you to do is please give you a minute to work on your own. Please graph this equation. I use EQN for equation. So on your coordinate axis that you've drawn on your paper, please graph the first equation, x plus y equals 2. If you need to do some scratch work to figure it out, that's totally fine, but I'll give you a minute to work on that. Does anyone want to volunteer their process? Like, how did you graph this equation? Yeah, Julie. Mhm. Mhm. Yeah, right. So and then connected the dots. And you can see, like, this is why it's kind of a sketch, because you can already see that because I didn't quite get a uniform space between everything, you can already see that it's not quite making a straight line, but it's pretty close, and it's just a sketch, right? So just to recap what I heard you say, you said you rewrote the equation in the form y equals 2 minus x. You realized that 2 had to be the y-intercept, so you graphed that point x equals 0, y equals 2. You realized that minus 1 had to be the slope. And when you knew that minus 1 was the slope, you said, well, if I go this way, then I'm going down 1, and if I go this way, then I'm going up 1. And that allowed you to draw a few points. You connected those points into a line, and then graphed it. Cool. So the next step in the guided meditation or whatever is, now that we've drawn our axis, we've drawn this other line. Please graph this second equation. And so this is only a sketch. It doesn't have to be completely perfect, because here you got these nice round numbers. Here, when you'll see that you don't exactly get nice round numbers, but just estimate to the best that you can. So any way you like, please graph this second equation. You could use any method that you like to graph it. Give you a minute to do that, and then we'll discuss. Okay, cool. After having given you some time to work on that one, this one I'll just explain. You can graph this the same way we did the other one. There's nothing wrong with that. But just so as not to do the same thing twice in a row, I'll show you a different method for this one. You really just need 2 points to make a line, and you can find those 2 points however you want. With this one, you might find it appealing to find the intercepts. Like if you want to find the y-intercept, you can set x equals 0. When you set x equals 0, this goes away, and you get 7y equals 9, so you get, therefore, y equals 9 over 7 as your x-intercept. So this is y equals 9/7 when x is equal to 0. Correspondingly, you can set y equals 0 and give you 2x equals 9. And if 2x equals 9, then x is equal to 9/2, or 4.5. And so you can just graph those 2 points and connect the dots. So how do you graph x equals 0, y equals 9 over 7? 9 over 7, you can put that into your calculator if you want, or you can estimate it. So I think of 9/7 as being like 7/7 plus 2/7. So it's like 1 plus 2/7. So it's like 1 plus, I don't know what 2/7 is, like 3.5/7 would be halfway up. So 2/7 is a little bit less than half. So it's sort of around there, you know. Not trying to be totally accurate. Or you could pull out your calculator. You could pull out your calculator and just say 9 divided by 7 is 1.285. So I don't know, wherever 1.28 looks like it is to you. 9/2 is a little bit easier. You go out on the x-axis by 4.5. So 1, 2, 3, 4, and then 4.5, around there. Got 2 points, you can connect those points into a line and maybe it looks something like that. So that's basically what I'm looking for, understanding that it's just a sketch. NASA is not going to be using this to create a flight path or anything, but it gives us an idea of what the two lines look at, and roughly speaking, where the two lines intersect. So like based on looking at that, does anybody want to volunteer? Roughly speaking, where do you think the two lines intersect? Yeah. Yeah, around here. And that could certainly be, it could certainly be, 0.87, like 1.2, so around there for sure. So our sketch is good, and it's sort of giving us an approximate idea, but maybe not knowing for sure what's going on. So let's say that we want to figure out exactly where they intersect. So the geometry is giving us an idea, and if we had graph paper, I bet we could really narrow it down. So the geometry way to solve this is to say, look, wherever the two lines intersect, that's going to be a solution to this equation and to that equation simultaneously. That's the geometry way of thinking about it, but there's also an algebra way of thinking about it, which says that if you just want to look at these two equations, perhaps we can manipulate those equations and arrive at an answer. And so, yeah, we can actually maybe solve these equations with elimination. From last semester. And anybody who remembers elimination from last semester, if you like, you don't have to. Do you want to volunteer? What might be a first step? Like a first step might be multiplying this equation by something. What might you multiply it by? Yeah. Yeah, sounds good. So if I multiply the first equation by -2, what's going to happen is I get, and what I mean when I say multiply the equation is of course I mean multiply both sides by the same number. If two sides are equal and I multiply both those sides by the same number, they'll stay equal. So 2x minus 2y equals -4. How did I get that? The left-hand side, -2 times x, -2 times y. The right-hand side, -2 times 2 is -4. And the second equation stays. So our goal is to find x and y that solve both equations at the same time. And you might start to think philosophically, what's actually happened here from the geometry side? Not much, because if you graph this equation, it's the same thing as graphing x plus y equals 2. Because think of how we graphed this. We solved for y and looked at the slope and the intercept. If you solve this for y, you'll still get 2 minus x, and the graph will be the same. It's kind of interesting to think about, that the graph of this equation is the same as the graph of the equation when you multiply it through by -2. It doesn't change anything geometrically. It's just a different algebra representation. But now, the point of doing this is that now we can add those two equations together. So x and y are unknown to us. -2x minus 2y equals -4. 2x plus 7y equals 9. You can add the left-hand sides together, you can add the right-hand sides together. I mean, these two things are equal, those two things are equal. You know, certainly I could add 1 to both sides, but I could add any two things that are equal to each other to both sides of an equation. It'll stay true. How do you add them together? You match up the x's and y's. Whatever x is, if I have 2 of them and I take away 2 of them, I'll end up with 0. Whatever y is, if I have 7 of them and I take away 2, I'll end up with 5y left over. And of course, 9 minus 4 is equal to 5. And so now, solving this by dividing both sides by 5, I'm going to get y equals 1. And so we're part of the way there, but we also need the x value. And how do you find the x value? Well, now that you've got the y value, you can plug it back in or substitute it back in to either equation. Just use the first one for the purposes of this example. If I take y equals 1, then I'll have x plus 1 equals 2, subtracting 1 from both sides, giving me now x equals 1, which is telling me that x equals 1, y equals 1 is the unique point that lies on both of those lines, which now starts to make sense. I mean, here was the point 1, 1 that we graphed, and yeah, in our picture, it absolutely does not intersect at 1, 1, but that's just because our picture is a sketch. Our picture is a sketch of what's happening. And because we're not, well, you might be better at it than me, but I'm not great at, drawing and getting the distances just right. I'm pretty good at visualizing the ideas, but I'm not so good at getting it, in perfect proportion. So the algebra helped me to discover that actually this point should be 1. Any questions on that? Yeah.
So pretty much just have to multiply the first equation by something that cancels out a variable on the bottom equation and then solve.
Yeah. And there's different ways to do it. Like, if you wanted to, I don't want you to think that just because I did it some way that that's has to be the way. So for instance, there's another way you could solve this. So you could have chosen, well, let me just ask you, is there another number other than -2 that you could multiply this top equation by to cancel something out? Yeah. So you could multiply top equation by -7 and arrive at -7x minus 7y equals -14, and keep that second equation the same. So the important thing to me is not that you use a particular constant to solve it, but the thing that's important to me is that we try to keep our work a little bit organized. So I start with the two equations together, and then I took care to rewrite those two equations, with the multiplication. So I try to make sure I show all of my steps. But now when we add these together, and I'm sure your idea, Rosie, for saying -7 was that now we're going to cancel the y values, or the y variable. So you add them together, and you get -7x plus 2x is minus 5x, 7y minus 7y is 0, and now you get -14 plus 9 is -5. And the cool thing about mathematics, is that there's no choice but getting the same answer, even though it's like expressed in a different way. This time you divide through by -5, arriving at x equals 1. Now, how do you figure out the y value? You go back and substitute into either equation that you like. Substituting into x plus y equals 2, again, gives you y equals 1. Finally conclude that that point of intersection is 1, 1. So one thing I think that's really cool about this, I think the coolest thing about this is the fact that there's like a geometric way where you can just see it, like 2 lines intersect. And there's an algebraic way where you can manipulate the equations to get the answer, represent the 2 lines with 2 different equations, and use elimination method to find the x and the y value. Let me give you one to practice. Or actually, even before I do that, did I lose my book somewhere? Oh, it's over there. Sorry. But even before I do that, I'll emphasize that, I mean, there's even other ways to do this that are like maybe less elegant, but they totally work, right? So I could take the second equation and multiply it through by -1/2, right? I could end up with x plus y equals 2, and then if I multiply this through by -1/2, I'd end up with negative x. So the -1/2 and the 2 cancel. Minus 7/2 y equals minus 9/2. And there's nothing wrong with doing this. It just gives you like an arithmetic problem that's a little worse than the other ones. But if you add the equations now, x minus x is 0. And I get y minus 7/2 y. What's y minus 7/2 y? Yeah. Yeah. I heard -2.5 maybe times y. A way you can do this with fractions is you can think that y is equal to 2/2 y, right? And so 2/2 minus 7/2 is equal to minus 5/2. So 2/2 y minus 7/5 y. What am I doing when I'm conceptualizing this? Like, so 2/2 times y, that's the same thing as 2y over 2. That's what we mean when we write something like this. 7/2 y is the same thing as 7y over 2. I wrote a 5 there, I meant to write a 2. So when you're subtracting now fractions with the same denominator, you can just do 2y minus 7y equals minus 5y over 2, or minus 5/2 y. Or if you like the decimals better, like you can do this in your head by realizing that 7/2 is minus 3/5, and so y minus, or excuse me, 7/2 is 3.5, so y minus 3.5y is minus 2.5y. Either way, totally fine. And then you're adding 2 and -9/2. So more fractions for us to add. 2 is equal to 4/2, right? So you can think of this as 4/2 minus 9/2, which would give you minus 5/2. Now you can solve this by multiplying both sides by minus 2/5, ending up with y equals 1, and then you're going to get x equals 1. So I don't recommend that you necessarily jump to that method because you introduced for yourself a little bit more arithmetic. It's kind of easier to take like something and multiply by a whole number than it is to multiply by the fraction, but it doesn't matter. It's all the same and it'll give you the same answer. So now let me find problem for you to do. Sorry.
Can you put, so when you solve for y after you into
Yeah.
equations?
Yeah. Yeah, you could plug into either equation. Let's do 8x minus 5y equals 11. Let's do 4x minus 3y equals 5. This time, no scaffolding. This time, please find x and y that solve both equations. So take a few minutes and then we'll discuss. Okay, after giving you some time to think, let's discuss through. Certainly there's a geometric approach to this too, namely you could graph the first equation, graph the second equation, and estimate the solution. Or if we're sitting online, we could plug both those into Desmos and sort of mouse over the solution anyway. But here, that's not what we're doing. Here, we're trying to use algebra to find the two things. So I'll take a suggestion from the class. Which equation would I like to multiply, and by what? Yeah. Sounds good. So when we do that, let's rewrite first equation, 8x minus 5y equals 11. And multiply what I heard was multiply the second equation by -2 with an eye towards canceling out x variable. And so -2 times 4x, that's minus 8x. -2 times minus 3y, that's 6y. -2 times 5, it's minus 10. And so now we have two equations. They're different equations. They communicate the same information. And we're thinking of adding these two equations together. So when I add these two equations together, 8x minus 8x is 0. -5y plus 6y is y. 11 minus 10 is 1. So I'm immediately led to y is equal to 1. Let me pause here and do something I didn't do previous time. So thinking geometrically, I've got a system of two equations, two lines. I'm searching for the intersection. I've now taken the second equation, multiplied it by -2. I've got two more equations. They represent the same two lines. So how does this business work with two equations? Because I sort of like added them together and just got one equation, right? So what you're thinking of doing is keeping the first equation fixed and then replacing the second equation with the sum. So like I can make a system of two new equations with still 8x minus 5y equals 11, and now y equals 1. So these are my two new equations. That's the way mathematicians think of it. We think of taking this system of equations, adding them together, and then replacing the second equation with this result. And what you get, like if you graph this now, one of your graphs is just y equals 1. So y equals 1 is just this horizontal line. This is the graph of y equals 1, and then x can be whatever it likes. And so this, if you graph this, this will like intersect here in a way that's like pretty easy to see the intersection. So that's kind of the geometric picture of what we're doing. We're manipulating the equations so that one of them is a constant, and it's easy to see the intersection. But instead of just going through and taking all the time to graph 8x minus 5y equals 1, you can just substitute y equals 1 back in here, and you'll get 8x minus 5 equals 1. Adding 5 to both sides, you'll get 8x equals 6. And dividing both sides now by 8, you'll end up with x equals 6 over 8, which is like 3/4. So my final answer is point of intersection is x equals 3/4. y equals 1. So around here. So even let me estimate the graph of this line, because if I know, like, if this line has slope that's positive, then it's, going that way. If it has slope that's negative, then it's going the other way. So like, what's the slope of this line? Like if I bring the 8x to the other side, it'll look like minus 5y equals minus 8x. Dividing through by negative 5 will give me a positive number. So it looks like this line has kind of like a general positive slope. So it looks, roughly speaking, something like that, if you just want to sketch it out. Any questions or comments on that? Cool. Would you like one more to practice, or are you good on systems? Or like, who knows? We've got a few minutes. Let's do one more. Let's do a word problem. This would be a nice way to close out the class. So you've got a rectangle. We start out with a rectangle with a given perimeter. So P for perimeter, and the perimeter is supposed to be 18 inches. So, I mean, eventually I'm going to work with two rectangles. Maybe I start with something that looks like this. It has a length, it has a width, and the perimeter is 18 inches. And perimeter, remember, does anybody remember what is the perimeter of a rectangle? What does this mean? Yeah. Yeah, that's right. So you're just looking at the length of the boundary, which is going to be length plus width plus length plus width. So 18 inches equals 2 times L plus 2 times W. And now the problem says, okay, now that you've got the first rectangle, a new rectangle is formed by doubling the width and tripling the length. So really I should call this W and that L, because now this, you could reasonably believe that this length is twice that one, and this length is twice that one. So perimeter with width, or rectangle with width and length, perimeter is 18 inches, it's 2L plus 2W. Make a new rectangle with twice the width and 3 times the length. The new rectangle has a perimeter of 46 inches. Okay, and so the question is, what are the length and width of the original rectangle? So L is equal to what? And width is equal to what? So take a few moments and work on that. It's related to what we've been talking about in class. And ask me any questions that you've got. Shall we discuss the problem? There's two equations. There's a system of two equations that we can solve. One of them is 2L plus 2W equals 18. That's the equation for the perimeter of the first rectangle. What's the second equation that we'd like to solve? Or that we'd like to add to this? Yeah.
Wouldn't that be 46 equals 3L plus 2W?
Almost. So 46 is the perimeter of this rectangle. And if you do 2W plus 3L, we've got half of it, right? But we still need like the other 2W and the other 3L, right? So I think we're almost there, but we need maybe 6L plus 4W equals 46. Does that make sense? Because for perimeter, we have to go all the way around all four sides. But now we've got a good strategy. We know we want to solve L and W with elimination. And, based on our practice with this, it seems reasonable to either multiply this by -2 to cancel out the W's, or multiply this by -3 to cancel out the L's. I'm going to try with -2. And the first equation is therefore going to be -4L minus 4W. A -2 times 18 is -36. The second equation stays like it is. It gives me 6L plus 4W equals 46. I want to add those two equations together. So -4L plus 6L is 2L. -4W plus 4W is 0. 36 -36 plus 46 is 10. So I get 2L equals 10. Dividing through by 2. It's going to give me now L equals 5. And in order to define W, I can substitute back into either equation that I want. I'll go ahead and substitute back into the first equation. So L equals 5 gives me 2 times 5 is 10, plus 2 times W is 18. Subtracting 10 from both sides gives me 2W equals 8. Dividing both sides by 2 gives me now W equals 4. So my final answer has to say something like the length is 5 inches. And the width, try to restate the answer in terms of the units of the problem, and the width, W, was 4 inches. So kind of cool, using elimination to find the original length and width of the rectangle. Any questions or comments on that? Thank you. Have a great day. No homework for tomorrow.